2, 1, go. Okay, so from the bell work today, what is chemistry? Well, chemistry is the study of stuff. Study of stuff. And the scientific word for stuff is matter. Matter is anything that has mass and takes up space. And what we're going to study about matter are these things. Its composition, what it's made up of. What are the parts that go into building it? Properties. What does it behave like? What does it do? What adjectives would you use to describe it? Because those adjectives that you would use to describe it are the properties. And the changes it undergoes. Most of us tend to focus on the changes it undergoes part when we think about chemistry, but if you don't know what the properties were to begin with, how can you tell they changed? Okay. Seem reasonable? Good. Okay. Now, people study chemistry for a couple of reasons. Some people study chemistry just because they want to know more about how the world around them works. It's called pure chemistry, where you're investigating for your only goal is to figure out how this little tiny aspect of the universe works. That's your only goal. You want to know better how this piece works. Gathering knowledge for knowledge's sake. Ooh, we learned this about the universe. Okay? And then there's applied chemistry. Applied chemistry is what you'd expect it to be. Apply the chemistry. Use it for a purpose. Use the chemistry to make new drugs for medicine. Use the chemistry to make new pesticides or new fertilizers for agriculture. Use the chemistry to make new materials for manufacturing new pieces. Or picking which material to use. What material would best suit these purposes. So you can either be doing chemistry to learn about the world, or you can be doing chemistry to solve a problem, a specific problem. Now, either one of these, there are chemists that do both of these. You got to pay them. They're working for a living. Which one of those people do you want to pay? It's the logical one is the applied one, right? I want to pay the person who's going to give me a product. But if you only pay the applied people, that's true. If you only pay the applied people, chemistry stops growing. You got to do the pure research so that you have things to apply later. So if you don't do pure, you'll have nothing to apply, so it wouldn't matter what the applied chemist did. So you need to pay for both. So at universities, they pay people just to study chemistry. The government pays them just to study how the universe works better. That's their job. Why? Because they also have people at the university that are trying to solve specific problems, and they may need that piece. They don't know what it's going to be useful for when they study it. Okay, the example is Bell Labs. In the late 50s, early 60s, there's a place called Bell Labs owned by the phone company, and they paid scientists just to figure out how the world works. And they found some materials that kind of conducted electricity. They could control whether they conduct electricity or not. And from those, they made transistors. And from those, they built a computer chip. But all they were studying was how electricity flowed through materials. They didn't have a goal of making a computer chip, because computers didn't exist when they were studying it. And the ones that were, computers they did have, were the size of rooms to do what your calculator does. Because they used big tubes to do the calculating. There weren't any transistors. So they didn't realize they were going to miniaturize the world into computers the size of the head of a pin. They didn't realize that was going to happen. They just wanted to know how things flew, how electricity moved through materials. That's all they wanted to know. But it led to transistors, which led to computers. Or they wanted to study about light, special kinds of light. So they found they could make light where every wave of it was in perfect sync. And when they did that, that light had special properties like it didn't spread out. It stayed together in a narrow beam. Okay? They made lasers just so they could study about specific kinds of light. They didn't realize that we would need them for our CD players right? Didn't realize that we could use them to measure distances across a room or to see how fast a car is coming at you. Got laser speed detectors for the police, so your radar doesn't go off. It's just a laser. All those applications they didn't think of. They were just studying light. So you've got to pay for both of them. Because if you stop paying for pure stuff, you don't have anything new to apply. And everything stops. Okay? So it's easy to say, I want to pay for applied. And lots of companies pay for applied. But some companies pay for pure, and the government pays for a lot of pure stuff so that we can apply it later. Okay? So that's what chemistry is. The other question on the bell today was, what is science? And I said the answer was, science was solving problems thinking like a scientist. And thinking like a scientist is the scientific method. You've studied it in several classes before. Hopefully I'll give you a different perspective on it. Okay? It's nothing fancy. It's just a way of solving problems, just an organized thought process for solving problems or answering questions. You use most of the pieces all the time. You just don't realize that's what you're doing. You do the parts of the scientific method without realizing it. And if you did take the time to realize that's what you were doing, you'd solve your problems faster. They say, oh, I'm trying to solve with the scientific method, then I should be pretty systematic about it. Okay. So what is the scientific method? Okay. It starts with an observation. An observation just means using your senses to figure out something, to notice something about the world. But you do more than notice it. What turns it into scientific, what scientific is, the fact that they have to write it down. To a scientist, if it's not written down, it doesn't exist. I had a former student that was doing some research at UCR, and he was getting ready to publish his paper. And he realized that one of his data points, he couldn't find that data point in his lab manual. He knew the number was right, but he couldn't find the number in his lab manual. So he had to repeat a month's work to generate that one number again. Okay? Because he didn't write it down the first time. They write down everything because they don't know what the important thing is. Okay? Then you've got a problem or an observation that's going to generate a question. And you answer that question with a hypothesis. So the question could be, why does that happen? Okay? So a hypothesis. Now in the past you've learned a hypothesis and they gave you a definition. Let's see if this one sounds familiar. A hypothesis is an educated guess. And while that's true, it's not good enough. I mean, if I tell you to pick a number, that's a guess, right? If I tell you to pick a number between 1 and 10, that's an educated guess. Is it a hypothesis? Okay, it's not a hypothesis because it's not doing this one. It's not an explanation. Okay, that's what's missing. Okay, it's a guess because they're not certain. So that's why I use the word possible. We're not sure if it's right or not. Explanation. And the educated part is you use research and previous knowledge. That's the educated. So the guess is the fact that it's possible. We're not sure it's right. But it's not some random guess. It's not pick a number between 1 and 54. Okay? See how it's different than an educated guess. It's about answering a question. It's about why. Why is the world this way? Okay? Once you figure out that, once you think this is the world is that way, then you design an experiment to test your hypothesis, to see if your hypothesis is right or wrong. This is the hardest part of doing science, designing a good experiment. Because if you design it right, it does that. It doesn't answer the question. It doesn't solve the problem. It checks to see if the hypothesis is true or false. Because a good hypothesis has only two possible results from an experiment. Possibility number one, the hypothesis is right. Well, they wouldn't say right. They would say supported. That hypothesis is supported. My possible explanation is still possible. And I believe it more because it worked this time. The other possibility is my hypothesis is wrong. The way they would say that is my hypothesis is rejected. So now I know my hypothesis isn't right and I have to change it. The problem we have is most oftentimes people design poor experiments. When you design a poor experiment, what you get is it doesn't tell me about my hypothesis. Yeah. But when you do the experiment, you're going to get data. And data is just observations from the experiment. And observations is where we started this stuff. We started with observation. So now we've got more observations to make a hypothesis about. So since we got new observations, we can get a new hypothesis, which means we can design a new experiment, which will give us new data, which will be the new observations, so I can make another hypothesis. So I can design a new experiment that'll generate more observations. Okay. What I'm trying to emphasize here is that science is not a line. You don't start and you end. It's a circle. And actually, what happens is you generate more questions than answers every time you go around. Okay. You talk to any scientist, they'll tell you that. So science isn't going to end anytime. Because when I learned scientific method, I learned problem, research, hypothesis, experiment, data, conclusion. One right after the other. But that's not how science works, because that implies that, oh, I'm done. We're done with that science. But no, we learned more, we got more questions than answers, so we need to go do some more new hypothesis, new experiments. Okay. To give you an example that you do this all the time, we just don't call it the scientific method, where it breaks down for you. Okay. Picture this. You go home from school today, sit down in the chair, pick up the TV remote control, push the power button, and the TV doesn't come on. You have a problem that you need solved. Okay, so we've got our observations. I push the power button on the remote control, the TV doesn't come on. Does anybody have a hypothesis based on previous experience that would explain those observations? The batteries are dead. Would dead batteries in the remote control explain why the TV wouldn't come on when we push the power button on the remote control? Is it the only explanation? Can anybody think of another hypothesis that would explain it? Blocking the signal because you got that little window on the TV. Is that the only one? TV's unplugged. There's lots of possible explanations why that TV doesn't work, right? And you're going to try a lot of things before you call a repairman. Okay? Okay. So you got a lot of possible explanations. So, but you can only test one at a time. So we have to pick one. So I'll pick the one that's most common. The batteries are dead. Okay. Now, design an experiment that would test the hypothesis that the batteries were dead. Be careful. This is where people make the mistake. What experiment could you do that would test the hypothesis that the batteries were dead? Okay. Most often, we say, you could put new batteries in. Okay. So I do that. That's my experiment. I put new batteries in. I push the power button on the remote control. the TV does not come on. Was my hypothesis correct? No. Let me ask that question differently. Were the original batteries dead? You don't know. You don't know if the original batteries are dead. So you got the third answer. Okay, so you'll notice what we didn't do. We didn't test the hypothesis. We tested the problem. And that's where science comes in. It narrows what you test. By making that connection, if my hypothesis is the batteries are dead, I need to do an experiment that checks the batteries. Does that make sense? Can anybody think of an experiment that would test that hypothesis? Is that? You know something else works, you put those batteries in and see if it works too. Okay. So you take the original batteries, you put them in a flashlight, hit the power button, the flashlight turns on. Was your hypothesis supported or rejected? Our hypothesis is the batteries were dead. It's rejected. We know the batteries aren't dead. But now we can come up with a new hypothesis because we've got more observations. When I push the power button on a remote control where the batteries are good, the TV doesn't come on. Do we have hypotheses that would explain that? Got one? The remote is broken. So you're saying the problem is the remote. Okay? How would you check that? Okay, another remote would tell you if the other remote worked, it would tell you something. But if it didn't, it wouldn't. Because you don't know if that other remote works.
Sometimes with certain cameras you can see if you shine that, if you look at the light through the camera, you can see if the light goes on.
Oh yeah, so because what the remote control sends is an infrared signal. It's a light wave we can't see, but it's right on the edge of what your iPhone can see. Regular cameras too, because it's right at the near infrared, so it's just barely below what we can see. But that would be, you can check to see if that light was coming on. Yeah. See, okay, press the power button on the TV, but remember, our hypothesis is about the remote. So what is testing the TV going to tell me about the remote? If the TV turns on, what does that tell me about the remote? It could still be a problem with the TV, because it may not be receiving the signal from the remote. The remote may be sending, but the TV's not getting. That's the hard part about this, is when you say what your hypothesis is, you've got to be really specific and test that hypothesis. What you're doing is, you see, we're trying to solve the problem. That's not how you solve the problem. You solve the problem by attacking the causes and eliminating them as you go. So I go to the scientific method when I try the simple fix and it doesn't work. And I say, oh, this is a hard problem. I need to stop and be really slow about how I do this. Why do I think this is happening? How can I check that? If I say it's the remote, I need to check the remote. Checking to see if it gives off the infrared light. That would be checking the remote. My remote lights up when I push a button. If it's working. The button I push lights up. That would be a way of checking it. See how this could help you solve a problem. But you got to be very specific about what you're checking between. Once you say what your hypothesis is, that's what you have to check. Okay, you're going to change things in your experiment, and those things that change are variables, because they're able to vary. You can change what they are. But we want to make it a controlled experiment because that tests our hypothesis. I want a controlled experiment where only one thing changes. You only want to change one thing at a time. The example, the place where you see it used most often is when they talk about testing new medicines. Okay. To test new medicines, they find people who have the condition they want to treat, they randomize them, and they give half of them the real treatment and half of them a fake treatment, a placebo. Because they learned that just giving somebody a pill will make them feel better whether that pill has anything in it or not. So you have to see whether it's the fact that you gave them a pill or whether that pill had drugs in it that made a difference. So they will do it and they give the treatment, and the doctor handing out the pills doesn't know whether they're handing out the real one or the fake one. Because if they know, it affects the results. They've learned in the past that by telling somebody which one they're giving out, it affects what results you get. So they don't even tell the doctors handing out the pills which ones are given. So the only difference is the pill. Everybody else, in every other way, you're treated the same, so that you know that any difference you saw was because of that pill. It narrows it to that. It's about narrowing in that hypothesis. Testing the batteries, not the remote. Make sense? Okay. So you're going to change some things. The things you change, your book calls the manipulated variables. For our battery one, it would be the type of equipment it's plugged into. That's what we manipulated. We picked what else to put it into besides the remote control. So the one you manipulate is the manipulated variable. One you change, you've manipulated it. Your book is the only book I've ever seen that called it the manipulated variable. The rest of the world is going to call it the independent variable. Now that seems backwards. If you're manipulated, are you independent? No, so it's got to be a different reason why it's called independent. It can't be about the fact that that it can't be independent in that context. There must be a different reason why they call it independent. Yep. So it literally comes down to not dependent. That's what the prefix "n" means, right? So you'll see it's not the dependent variable. Okay. So the responding variable is what changes as a result. And it's the thing you don't have direct control over. Whether the people got well from the medicine, nobody directly controlled that. We hope the medicine made the difference. So it's what you don't have direct control of. That the scientist doesn't manipulate, they're changing this, but something else changes as a result. And that one's called the dependent variable. It's named right. It depends on what happened. It depends on what you changed. So the other one's called independent because it's not the dependent. So manipulated is independent, responding is dependent. Two sets of names for the same concept. Okay. So this is how you should be picturing the scientific method now. Observations are explained by hypotheses, which are tested with experiments that generate observations that are explained with hypotheses that are tested with experiments. Sheridan went home today, so we've got a cycle. and it repeats lots of times. Okay? Other people will be studying the same stuff you are. They're going to be doing experiments around the stuff you're studying too. So they've got their own cycles. They're going to share their information with you, share what they've learned. So over time, that explanation for why things are happening, every time it goes through this loop, either gets more certain or gets corrected. So that hypothesis gets better and better. You become more certain of it because it explains more things. Okay? And when it explains lots of things and has been tested lots of times and it keeps working, they stop calling it a hypothesis and change its name to theory. So a theory is a grown-up hypothesis. After lots of testing, a hypothesis becomes a theory. When it can explain more things, a hypothesis becomes a theory. The problem we have with the word theory is that other people use it in other ways. Lawyers, social scientists, they use theories, and their theories are just possible explanations of why the crime happened or what happened and what the people were thinking in that historical time. The cause of the Civil War. There's theories about the cause of the Civil War. Which one's right? Is data going to prove anybody right? Nah, it's opinion-based. So in the social studies and law, theory is just somebody's idea. In math, theorem is absolutely true all the time. If you take that theorem and follow it backwards, you'll come back to one of the 6 statements that starts math. All of math starts off with 6 statements, and everything can be traced back to those 6 statements. Everything's proven from those statements up. You know, all those little proofs you're doing now, they did all the way to prove 1 + 1 = 2. It's built into the rules of math. One of those 6 rules. Okay? So theories and theorems in math are always true no matter what. Science, the word theory is in between those two. Okay? So what do you mean in between those two? Well, you'll hear this statement. A theory can never be proven. A scientific theory can never be proven because proven is a math word. And math words mean always true all the time. There's no way it can't be true because it's all just logical thought. It's not about the world, it's about logical thought. Okay? But the fact that we say can't be proven doesn't mean that we're unsure of it, because by the time it gets to be called a theory, it's explained everything you've seen. So you're not sure of it. It's not that you're not sure of it. You're sure that this is how it works, as far as you know, but you have not seen everything in the universe yet. Since you haven't seen everything in the universe, you're open to the possibilities there's something that you haven't seen that will change your idea about how it works, but you don't expect it. So usually you hear it in the context of it's only a theory. In the context of evolution. Oh, evolution is only a theory. It's only the best explanation. It's only explained everything you've seen. That's all it's done. Well, that sounds pretty powerful to me. To give you an example of what we mean by it's only a theory. And we're all made up of atoms, right? Atoms are only a theory. They are only the best explanation for everything we can see happen. Do you think scientists doubt that there are atoms? Do you think scientists doubt at all that there's atoms? No, they don't doubt that it's there. But they wouldn't say that atoms are proven, because proven means we're not open to anything about the atom changing. And we've got a lot more to learn about the atom. Okay? So when somebody says it's only evolution, or it's only a theory about evolution, they say, oh, atoms are only a theory too. How doubtful are you of those? So theories mean they've been tested many, many times and have worked that whole time. That's what theory means. Okay, theories are useful because they predict behavior you haven't seen before. Okay? They're useful because they predict behavior you haven't seen before. Hey, if they predict behavior you haven't seen, you can experiment on them. When it's a theory, they still check theories. They still are doing experiment because it's the hypothesis you test with the experiment. The theory you test with the experiment. A theory is just a hypothesis that grew up. Okay? They help us form mental pictures of processes and things. Like the picture you have inside your head of an atom is your theory of the atom. It's another name for that theory in pictures is model. Sometimes it's in pictures, sometimes it's in computer simulations. The models they use for the atmosphere to do weather is computer simulations based on what's happened with the weather in the past. So a model is just a theory in pictures. So that's where theories come from. Theories come out of hypotheses. Okay, another outcome is that a certain behavior is repeated over and over again. You're going to do lots of experiments. You're going to have lots of observations, and you're going to see patterns in those observations. Oops. What's going to happen the next time I let it go? It's going to fall, right? Why? Okay, because of gravity. Why is there gravity? Oh, it has something to do with the Earth's mass. Earth's mass helps us figure out how strong it is. But it was a trick question for me to ask you why there's gravity. Because scientists don't know. There is no theory of gravity. They don't know why gravity exists. They know it does exist. Fact is, one of the first patterns they recognized was the law of gravity. Isaac Newton discovered the law of gravity. Okay? So one of the first laws we came up with, what happens? We have no explanation for why it happens yet. That's kind of strange. I thought gravity was pretty well understood. It's not understood at all at the most basic level. We know what's going to happen, but we don't know why it's going to happen. So why is a hypothesis or a theory? What is a law? What happens is a law? Okay? Laws are measurable. I could measure how fast things fell. Fact is, the law of gravity is not that things fall. I mean, because if you hear the story about Newton discovering the law of gravity, they always have him underneath an apple tree. And an apple falls. Did apples not fall before Newton sat underneath that tree? Then how come he gets credit for it? Well, because he gets credit for it because he realized that the same thing that was pulling the apple to the earth was keeping the moon from flying away from the earth. He showed that the force that was causing the apple to fall was the same force that was pulling on the moon to keep it going around the earth. That gravity was universal, that everything had gravity. So it wasn't about one specific experiment, it was about the results of lots of experiments. Okay? It's measurable. How fast it falls is measurable. Laws are usually equations, mathematical equations. This is the actual law of gravity. The force between any two objects is equal to g. It's called the gravitational constant. It's a really tiny number. I think the number comes to mind is 10 to the negative 19th. That's 18 zeros before you get to the first digit. Point, then 18 zeros. So a really tiny number. Times the mass of the first object, times the mass of the second object, divided by the distance between them squared. So this says any two masses will feel a force related to how far apart they are squared. Do you have mass? So do I. Hey guys, you're all attracted to me. Y'all feel it? No, you don't feel it. Why? Because I'm not quite that big. Okay? Because this number is really small, we don't feel gravity until one of these numbers gets really big, like planet-sized. The way we feel gravity, one of these numbers is the Earth. The mass of the Earth times our mass. That's why we feel it, is because the mass of the Earth is so big. Okay? But it says every two things in the universe attract each other. It's technically the law of universal gravitation. Why do they attract each other? They still don't know. But they came up with this in the 1600s. It was one of the first scientific laws they came up with. We still don't know why. Okay. But that's the distinction between laws and theories. Laws are about how things behave, what they do, how hard they're pulled. Theories are about why they do what they do. What I run into is people someplace got trained along the way that the difference between law and theory was certainty, that one of them was more certain than the other. And they're exactly the same certainty. A law has described everything that happened so far. A theory has explained everything that's happened so far. As soon as they see something new, they'd have to change the law or the theory. Either one. If you have something behave in a new way, your law was wrong. And apparently your explanation was wrong too, because it agreed with the first one. So the difference between law and theory is not about certainty, it's about what question you're answering. What versus why. Homework is page 34 on the board. It's always on there for Due Thursday. Okay, it's on School Loop. Have a pleasant afternoon.